Today we will discuss about code converters. So code converter is also a combination circuit which helps you to convert a particular code to another code. Okay. So various examples of code converters are you can design a logical circuit that converts a binary number to BCD number. Similarly, you can design a code converter that converts binary to gray code and the vice versa, that is gray code to binary. And another example is binary to XS3 code and the vice versa, XS3 code to binary. So these are the various examples of code converters. So first we will see how you can design a code converter that converts a 4-bit binary to 4-bit gray code. Okay. So before going to design procedure, you need to know what is this gray code and how you can convert a binary number to gray code. Okay. So binary number to gray code can be done as it is shown in the figure. That is, if you represent a binary number as 10110, then its corresponding gray code can be found out as the first bit, that is the MSB bit of the gray code represents the MSB bit of the binary number itself. That is, the MSB bit of the binary number is 1, hence the gray code also the MSB bit will be 1. Okay, and the second bit of the gray code can be found out as XORing the first two bits of the binary. That is, the first bit MSB bit XORing with the next bit will give you the second bit of gray code. Similarly, the third bit can be found out that the XORing of second bit and third bit of binary. Similarly, the fourth bit can be found out by XORing the third bit and fourth bit of the binary. And the last bit, fifth bit, can be found out by XORing the fourth bit and fifth bit of the binary number. Okay. I will write another example for this conversion. That is, if my binary number is 1110, and how I can find out this gray code of this corresponding binary number is that your first bit of gray code will be nothing but the first bit of MSB itself. So this is written as such for the gray code. And then next bit of gray code is XORing this bit and this bit. So 1 XOR 1 is 0. And then next bit is this 1 XOR 1, that is also 0. And the next bit will be this 1 XOR 0, that will be 1. So 1001 will be the gray code of 1110. Okay. So this is how you will convert a particular binary number to its corresponding gray code. Now we will move to design procedure. So how you can design a 4-bit binary to 4-bit gray code converter. So the first step for the design procedure is to write the truth table where the input represents your 4-bit binary number and the output represents your gray code, which is in 4-bit. So just write the corresponding gray code of this input. So since there are 4 bits, you will be having 2 raised to 4, 16 combinations of inputs starting from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so how will you find out the corresponding gray code of this input 0, 0, 0, 0? Just take the XOR of the bits. That is, the first bit will be 0. Next bit will be 0 XOR 0, that is 0. Again 0 XOR 0, that will be 0. And 0 XOR 0, again 0. So G4, G3, G2, G1 represents your gray code having the bits 0, 0, 0, 0. Okay. Similarly, next bit 0, 0, 0, 1, you will be converting that binary number to its corresponding gray code. Okay, that is 0. Then 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. So it is 0, 0, 0, 1. Similarly, you'll be filling all the inputs. All the inputs and the corresponding outputs are obtained. Now you're going to find out what is the expression for G4, G3, G2 and G1 by drawing the Karnaugh map for the corresponding bits. You will be writing the Karnaugh map for G4, plotting the ones for the minterms. Then you'll be drawing the Karnaugh map for G3 and find out the equation for G3, similarly G2 and G1. Okay, so when you plot G4 on the K map, it is found out that the minterms 8, 9, 10, 11, 12, 13, 14, and 15 give you the value 1 for G4. So G4 can be written as sigma m 8, 9, 10, 11, 12, 13, 14, 15. And when plotted that on the K-map and grouped, you got G4 is equal to B4 itself, isn't it? That is, when you analyze the G4 bits as well as the B4 bits, they are same. When B4 is 0, G4 is also 0. When B4 is 1, G4 is also 1. So you can see that G4 is nothing but B4 itself. Okay, that is what we have seen before. That is, G4 is nothing but B4 itself. Now, you are finding out the next bit, that is G3 bit. G3 bit, you are plotting the min terms having 1 on the K map, and you found out that when grouped, we will give you B4 dash B3 plus B4 B3 bar, that is B4 XOR B3. The binary bits, fourth bit and third bit, when XOR will give you the third bit of gray code. That is how you obtained here also. That is the B4 and B3 bit XOR will give you the B3 bit. The same equation you got from the K map also. And then G2 is the minterms plotted with 1 on the K map. The G2 values will give you B3 XOR B2. Similarly, G1, when the G1 minterms that give you value 1 plotted on the K map will give you the G1 value as B2 XOR B1. So these are the expressions. G1 is B2 XOR B1, G2 is B3 XOR B2, G3 is B4 XOR B3, and G4 is B4 itself. Now the next step is you have to draw the circuit diagram for representing these equations. That is this. That is, your input will be binary and output is gray code. So input bits are B4, B3, B2, and B1. So B4 XORed with B3 will give you G3, and then your B3 XORed with B2 will give you G2, and B2 XORed with B1 gives you G1. This is the converter circuit that converts. It's the code converter circuit that converts binary input into corresponding gray code. So that's it.